Hello, everyone. My name is Anthony Feldman. I'm a PhD candidate in the Department of Geosciences, and today I'm going to be presenting to you on a project of mine looking at the use of buried olivine samples in terrestrial soils as potential indicators for past water-rock interaction conditions on the surface of the planet Mars. So olivine is a magnesium and iron-rich silicate mineral that is common both on Earth and on Mars, very common in the interior of Earth, and very widespread on the surface of Mars. Now, we're interested in olivine because many dissolution experiments in terrestrial labs have indicated that olivine has a very rapid rate of dissolution when in contact with water. So its widespread presence on the surface of Mars might be an indication for limited durations of water-rock interaction, or be able to tell us something potentially about the chemistry of the water that was present on the surface of Mars. Now, most of the dissolution experiments that have been conducted on Earth have involved magnesium-rich olivine. But this figure on the right over here is showing you a range of olivine compositions that are predicted for the surface of Mars, and they're very highly fayalitic, or what we know as iron-rich olivine. So what I'm doing with this study is looking at the persistence of natural olivine in very magnesium and iron-rich soils on Earth, and then also burying synthetic samples of magnesium-rich olivine or Forsterite and iron-rich olivine known as Fayalite, and examining their alteration over the course of 1 year to see whether we can backtrack from the kinds of alteration characteristics we see to the chemistries of the fluids that are reacting, as well as the environmental conditions present. So the field sites that I'm investigating are spread around North America, in Newfoundland, Canada, called the Tablelands, in the Klamath Mountains of Northern California, and a site called Pickhandle Gulch near Tonopah here in Nevada. These sites are primarily differentiated by climate. So the Klamath Mountains are a Mediterranean climate with a wet winter and a dry summer, as we can see in this mean precipitation graph on the top right over here. The Tablelands have a subarctic climate, which is wet year-round, and Pickhandle Gulch has a desert climate, which is dry year-round. Now, in addition to that precipitation regime, these sites are also differentiated by mean temperature. So the Klamath Mountains and the Pickhandle Gulch sites are relatively warm, with mean annual temperature conditions of 12.8 and 14.4 degrees Celsius, respectively. And the Tableland site, again subarctic, is very cold year-round, with mean annual temperature conditions of about 3.9 degrees Celsius. We also have one other environmental differentiating factor here, which is the soil pH, or a measure of soil acidity. The Klamath Mountains, highlighted in red in the figure on the right over here, are circumneutral to slightly acidic. The Tableland soil conditions are roughly neutral to slightly basic or slightly alkaline, and the Pickhandle Gulch soils are more alkaline, with a mean annual pH of about 8.5. Now, the Klamath Mountains and the Tableland sites are also interesting for their natural olivine because they have differences in soil age derived from deglaciation during the late Pleistocene or over the last 50,000 years, with soils in the Klamath Mountains ranging in age from about 12,000 years to about 50,000 years or potentially older, and in the Tablelands, soil age ranging from about 13,000 years of age to about 25,000 years of age. Now, when we investigated natural olivine in these soil environments, we used a technique called X-ray diffraction, and it takes powdered soil material, bombards it with X-rays, and we read the scatter of those X-rays to produce these figures that we see in the graph here, where peaks in these lines correspond to internal planes within the minerals in the soil system that we can use to fingerprint or ID the mineral content of the soils. And so I've labeled peaks in each of these soils that correspond to the presence of olivine. And what we can see on the left over here is that in the Klamath Mountains, that warmer Mediterranean climate, olivine only persists in the soils that are of 12,000 years of age, but is absent from the older soils, indicating complete dissolution. Whereas in the Tablelands over here, even though the peaks attributed to olivine are much less visible, indicating a lower overall content, they persist in all of the examined soils up to the oldest soil, which is, again, older than 20,000 years of age, likely 25,000 years of age. And so we can already see climatic differences where natural olivine is persisting much longer in that colder environment, even though it's a wetter environment in the Tablelands. So after looking at this natural variation, we wanted to see whether we could observe variations in incipient alteration and whether we might be able to use these incipient alteration characteristics to gauge the kinds of water chemistry and environmental characteristics during alteration. So we performed a burial experiment where we buried synthetic olivine samples in these same soils and analyzed them visually and spectroscopically. So in order to create these discs, we fused together magnesium-rich olivine, Forsterite, and iron-rich olivine, Fayalite, in our lab here at UNLV. And you can see images of these discs on the right. And then in order to get pristine surfaces that will then be altered after emplacement, we polished these surfaces using diamond grit to a 1/4 micron polish level. Our burial methods, so we went out to the same soils that we acquired our natural olivine samples from and buried these synthetic discs of Forsterite and Fayalite for exactly 365 days or 1 year. They were recovered, washed gently with ethanol in order to remove any adhered soil particles, stored at -20 degrees C in order to limit any potential further alteration after acquisition. We then analyzed these techniques using scanning electron microscopy, which is a direct imaging technique, X-ray photoelectron spectroscopy, and a technique called visual and near-infrared spectroscopy, which is also able to be employed by the rovers on the surface of Mars. So what I'm showing you in this image right here is scanning electron microscopy imagery of those magnesium-rich Forsterite disk surfaces, as well as a control disk, which was created but then left unweathered in the lab at UNLV for comparison purposes. So these magnesium-rich disks exhibit a direct 1-to-1 correlation with environmental conditions and soil pH. So that control disk over here has a completely flat surface. All of those divots are just a result of the polishing process creating some very minor but angular divots in the surface that are easily recognizable in the other imagery. This pick handle gulch surface here exhibits no formation of dissolution features, shallow pitting, or dissolution lining. The tablelands disc right here, we've labeled the formation of some shallow pitting features and dissolution lines, and the Klamath Mountains disc we're showing you over here has much greater visual evidence for the formation of these dissolution features. So we can see this progression from that dry, arid conditions at Pick Handle Gulch to those wet conditions in the tablelands in the Klamath Mountains, and then the warmer and wet conditions in the Klamath Mountains exhibiting the greatest amount of dissolution. So we see this correlation with temperature, pH, and precipitation trends. However, while we see some correlation in the Fayalite or that iron-rich olivine in these visual SEM imagery, we don't see the same correlation. Pick Handle Gulch and the Tablelands disc exhibit a similar correlation with less alteration in the Pick Handle Gulch, more alteration in the Tablelands, but we see a basically unaltered surface for the Klamath Mountains. So something else must be happening here because we don't see the formation of similar lining or dissolution pitting features in the Klamath Mountains Fayalite disc. So we also examined these disks with X-ray photoelectron spectroscopy, which can analyze cation content in the upper 10 nanometers of the disk surfaces. Silica is a relatively immobile element, while magnesium and iron are relatively mobile. And so we can get a look at whether these magnesium and iron cations are being leached or deposited onto the surface using this technique. And in the Forsterite, those disks that did correlate well with environmental conditions, we see leaching of magnesium from the Klamath Mountains and Tableland surfaces, but we see a relatively pristine magnesium to silica ratio of 2-to-1 in the Pick Handle Gulch disk. So again, we're seeing that dissolution both in the imagery and in this spectroscopy technique. In the Fayalite discs, we see a 1-to-1 or stoichiometric ratio in the Tablelands disc. So we likely have we might likely have stoichiometric dissolution that isn't preceded by leaching. In the Pick Handle Gulch disc, we do see some leaching to accompany that dissolution we saw in the imagery. Whereas in the Klamath Mountains disc, that relatively unaltered or undissolved disc, we see greater iron content. So this might indicate that we see something like deposition of an iron oxide layer on the surface that's preventing further dissolution of the disk surfaces. We also analyzed these disks using VNIR spectroscopy, a technique available on the Mars rovers, but this didn't show any real visible alteration of the disk surfaces, confirming that in this incipient alteration, we have these dissolution features, but we're not really seeing secondary precipitates on these surfaces just yet. And we can see that in these images on the right over here, where the black lines are from the control disks and the green, red, and blue lines are from buried samples. We really don't see any change from those control disks. So again, we don't see precipitation of secondary materials. Now, what does all of this imply for Martian dissolution and water rock interaction? Well, long-term natural persistence of olivine suggests that olivine presence on Mars is consistent with limited durations of water rock interaction, cool temperatures, and basic or alkaline reacting fluid pH. Our incipient alteration experiment does suggest that Forsteritic olivine or magnesium-rich olivine correlates well with environmental conditions, but we need to pursue more experiments looking at Fayalite to try to understand why it doesn't exhibit these same trends. But again, olivine weathering likely does yield important information about environmental conditions during alteration. Thank you.